So in practice, we didn't use gradient descent, or we also didn't using stochastic gradient descent. In practice, we use Minibatch SGD. So we already talked about the Minibatch SGD, but here gives some examples how the batch size can trade off, like convergence rate and computational time. So here we use a very simple data set. Like you have about 1,500 examples and only 5 dimensions. So that's a pretty simple data set. And kinds of implementation, I'm going to skip it because we already have given SGD how to update. Just get the learning rate and get the gradients and and update the parameter. That's all about SGD. And also, I probably going to skip this training function. It's nothing different as we had before. For each epoch, computer gradients, update the parameters, compute a loss function. The only difference probably we just visualize, we visualize the training progress. Okay, so this is a training function. We given the learning rate, we given the batch size, and specify the number of epochs. Now we will see, given different batch sizes, given different epoch, what is training progress. Firstly, because we know that the number of examples is equal to 1,500, if we specify the batch size equal to the same, which means it's just a gradient descent. Now we use the learning rate equals to 1, and the batch size equal to number of examples, and run 6 epoch. Now you can see that the final loss is 0.24. And each epoch we take about like pretty fast because it's tiny data set, 0.01, like 0.02 seconds. That's runs pretty fast. And remember, this is the convergence. X-axis is the number of epochs, and the y is the loss. And we want to compare this one to all these other different algorithms. Okay, so now how about SGD? For SGD, we just pick batch size equal to 1. And we're using much smaller learning rate. Because we have not noise, we need to do a little bit decrease the learning rate here. You can see that firstly, well, it doesn't decrease. Sometimes it increases the object function. In the gradient descent, we show that we given proper learning rate, we always guarantee we can decrease the object function. But on SGD, usually not the case because we have so many noises here. On expectation, we will decrease the object function, but not in practice. Also, at the end, you can see that like little bit of trouble here. Now you have, at the end, actually suffer a little bit here. But still, in terms of number of epoch, the convergence rate is much faster. Like at 0.5 epoch, we almost are close to the final results. Comparing to gradient descent, until to like epoch maybe at 3, almost reached the optimal like solution. But for SGD, 0.5 epoch, we almost match the results. Okay, so this kinds of, because in SGD we make so many updates. And before each epoch, we only think single update for gradient descent. SGD, for each epoch, we make thousands of updates. Question? Yeah. But the other thing you want to see that is that we take 1.4 seconds for each epoch. The number we have, 0.0, almost a 2. Two problems. One's because SGD make more updates, so that's make more like computation. The secondly, each one we only compute a single example. The workload is pretty small, and it's hard to be parallel because you don't do matrix multiplications. Now you do matrix vector multiplications. Also, because of Python, in the for loop you have a lot of overhead. So all the things make SGD much harder to compute for each epoch. So Minibatch SGD trying to balance the trade-off. So here we use 100 batch size. For each batch, we process 100 examples. Now, still the convergence rate is very similar. With 0.5 epoch, we are pretty good, close to the final solution. But now the time is much faster, 0.04 second for each epoch. Okay, so because of the batch size is larger, and each batch we are doing more efficient implementations, and also we have less Python overhead here. Okay, how about another one, like using 10 epoch? And the convergence rate is still very similar. Like at 0.5 epoch, it's pretty good, decent results. But like again, it's the number of batch per iteration is smaller, and it takes more time for each epoch. It's 0.14 here. Okay, the idea is that using Square SGD or Minibatch SGD, usually we can make it converge faster in terms of number of examples we processed. But the computational cost varies, depends on the implementation and a lot of other things. So what we can do here, we can actually compare all the things. Well, this fake, let me just remove. The basic idea is that we have all these results we visualize in the single fig. And the x-axis is the time, second. The y is the loss. So firstly, you can see that the blue line is the gradient descent. Okay, and after single epoch here, you actually have very good loss, but convergence not so great at the end. On the SGD, we know that it converges very fast, but it's pretty slow in terms of time versus loss. SGD doesn't win here. How about batch size equal to 10? Well, improve SGD a lot because the computation is much more efficient. The convergence rate doesn't change too much, so which means this is a big gap from simple SGD to mid-batch SGD with batch size 10. We further improve it using batch size 100, and it's a little bit slow at the beginning, but at the end, actually, it's outperformed the gradient descent. The reason is because for mini-batch SGD, for each epoch, we make about 15 number of updates. So if you make so many updates, make converge faster, and the computational overhead is not so bad. Like every time we process about 100 examples, the efficiency is decent. So we just sum this thing together, so the mini-batch SGD actually win the gradient descent. Okay, in practice, in deep learning, so here we use a very tiny example. So the gradient is much easier to compute. And in practice, for deep learning, so mid-batch SGD usually is much better comparing to gradient descent, because computing the gradient over the whole data set takes maybe a few hours in large-scale data set. Also, it's less sensitive to the batch size. Batch size 32, but batch size 64 doesn't give you like 2 times speed up, usually 0.20% difference. But batch size equal to 1 to batch size equal to 32 maybe give you a little bit difference, maybe up to 2 times difference. So in practice, we usually make the batch size large enough so that we get good computational efficiency. And still, once you get it, let's look at the convergence rate. Don't make the batch size too large. Now, on the extreme case, you make a gradient descent, it converges much slower. So that is kind of a practice trade-off for how to choose the batch size. Okay. And we probably skip the Group implementation. We know how to do that. Okay.